before diving into the RTOEFL, I wanted to in the last video break down the TOEFL myself. So this would be this gate, and I didn't really get into quickly into something in the video, so I did it afterwards because I just couldn't wait. And I didn't get basically a really optimal solution because it's still you still have control controlled controlled like square root of x gates, or you could also then reframe it to control t gates. Um, so that's still not ideal in terms of using a set of gates that it's directly available on a quantum computer. But it was just worth the exercise, and I think I won't go farther with that. I'll just see if that helps me with understanding the art of. So, but basically, I'll just walk you quickly through what I quickly, what was my mental process. Basically, I kind of realized that one way that uh, one way that we could do it is sort of with partial rotations, right? So the way that I started was good. So if what we want is we want to have a full NOT gate applied down to this qubit, if both these elements are one, um, why don't we build it like progressive, in the sense that, so if there's a one in here, that's going to contribute half a rotation, right? If there's another one in here, that's going to contribute another half a rotation, and then we're done, right? So it's like, cool. So here you have that. Of course doesn't work for the other inputs 0 1, because you still have, so you've got half rotation, but you basically gotta correct these ones somehow, right? So and basically the way that I went about this was, okay, so let's see um, if we've got a 0 in here, right, then we should correct that. But that's not completely true, because if I just would go like that and do this and say if there's a 0 in here, because that literally that would be the same as using in Quirk this one, right? But let's use this notation. So if I would do something like that, that's still um, so it works for this case, but it doesn't, like, in turn this doesn't work for this case, because it's undoing something that it shouldn't be undoing, because we haven't really done anything here. So like this control square root hasn't really of x hasn't really happened, so you don't need to correct it. So one way that you could do is you could say, no, you can control for the full case, right? So for the full for the entire input set. So you could say, no, if, and that basically is turning this into, if you've got a 1 0, right, apply that correction. So that works well for this case. Now if we've got this case, the 1 1, it still works. And remember, if we get it to work for all the single amplitude type of inputs, it should work for anything else, for all the superpositions and stuff like that, because it's sort of a built-in feature of the quantum computer, or the simulator in this case. It just linearly works. It combines. So, but then I was like, okay, so this works for these, but then if I got this case, uh, 0 1 0, so that works. That works. Wait a second, did I just did I just find something that actually works and it's shorter? Is that my original solution? Because I went farther than that. Oh, wait a second, it might not work. So this is 0 0 0. this case is 0, 0, 1. In this case it's 1, 1, 1, that's correct. And in this case it's 0, 1, 0, that's also correct. Because I was gonna say basically you can you could also say that they need to implement the opposite case in here, but you don't really need to, like as in doing like that, right? And saying, okay, so if you've got like a 1, 0, you want to correct that as well. But you don't have to, because if you've got like a 1, 0 in this case, this is applied, and then this is corrected as immediately, because basically that doesn't happen. Oh, that's interesting. Is this really equivalent? And if I just do 1, 1, 1, so yeah, that seems to work. How could I compare? Yeah, how could I compare whether this is equivalent or not? That's an interesting thing. So would I just need to maybe calculate the matrix of that and then compare it? Okay, that seems to work. Now, I'm not so sure if this is. So what if I do something like this, a minus, right? As the input state, and shouldn't I see here some phase kickback? Shouldn't I see some phase kickback in here? So if I take a look at the amplitudes here, of these versus these, yeah, there is. So 1, 1, 1, that has a phase of 0. If it's a minus, that part has an 180 degrees phase. And so because I would assume that exactly, so it does have that phase goes up here. I don't know if that's it, but this seems to be okay. This seems to work. You could. Don't get me wrong. I'm not good at this, so that might not be correct. But I was now gonna explain the whole thing, and it's like, wait a second, that actually works already. You can basically turn this into control T operations if you just basically replace it, like sandwich this with Hadamard's and then replace not with T, that would be S actually. Those would be controlled S operations. So, and that should give you the same effect. If you go this way, that should give you the same effect. Yeah. Minus minus. If you go minus minus, like what do you have? So you're gonna have a negative phase there where there's a 1. But here in both cases they cancel. No, they don't. It's not that they cancel, but you got 180 degrees relative phase per input qubit, so it goes back to 0. Okay, interesting. So this is one way to do it, I guess, but it's not optimal or ideal. So, but I don't know. It's a combination of these things. But you can see the pattern here would be that you use your, let me go back, that you're using your input to basically do a portion of your target gate in here, and you undo it in the cases the input doesn't match what you want to do. So you're kind of doing half an X gate and then undoing it for those cases where it doesn't work. Okay, so now let's move on with this. Let's move on with this. So here, the trick here was basically, after executing the oracle, we perform normal diffusion operator for Gauss algorithm as described in section 2. Therefore, we discussed how to implement an n-controlled X gate under the constraints of the IBM Q processor. To construct n-controlled X, we introduce, to construct these like n Toffoli, or how you want n-controlled X, we introduce the relative phase Toffoli gates, RTOF. A Toffoli gate is known to require 5 controlled unitary gates for 6 control X gates, or 6 controlled X gates. 5 controlled unitary gates. How many we got here? 1, 2, 3, 4, 5. Yeah. And those are controlled unitaries in this case. So you don't. It's like, okay, so they're controlled unitary gates. Okay. Or 6 controlled X gates. So I guess there's another implementation where it's just control X gates. But then you need some extra. Okay. Man, I can't I just I wanted to explain. Let me know. I have to do this. Give me a second. Can I just screenshot that? I'll just screenshot that. No. I'll put like a. So I'll screenshot that and let me go to Twitter, because I basically tweeted that. Lol, just realized you can reduce this circuit a lot while doing part 7 of the series. Seems to work. So let's see if that. Let's see if that's. Yep. Okay, cool. And this matches the this matches this part in here. So it's almost like a Toffoli gate recurring only. So, but RTOF, let's focus on that finally. RTOF works almost like a Toffoli gate, requiring only 3 control X gates. In compensation for the reduced number of control X gates, an undesired phase is added to the target, which must be compensated for later. We adopt 2 types of RTOF shown in figure 9. Both of these RTOF can be implemented on a system with only a one-dimensional qubit layout. Although the number of control X gates is equal, RTOF, so there's 2 types, RTOF M and RTOF IX, does not require U3, which reduces single qubit rotation errors. Okay. We also introduce a Toffoli gate with built-in swap operation. Okay. Okay, so a Toffoli gate basically does Toffoli and swaps the thing. Okay, but let's focus on this first. So what is going on here? So we've got, let's build that here, clear circuit, and then let's see So it's a okay. So we've got a Hadamard, then we've got a T, and then we've got a control knot, and then we've got a T dagger, and then we've got another control knot, another control knot, T T dagger H. Okay, so yeah, here and T dagger, and then Hadamard. So okay, so we see that is the same pattern that we're getting, but there's this is faced by 90 degrees. When okay, when I take a look at that subsystem, seems to be there's some nasty entanglement in here, and so we can't really. Okay. So I can't really take a look at the phases in here. But let's break this down. Maybe let's start from like this 1 1, the 1 1 case. So if it's the 1 0 case, yeah, okay, so it works really. It just adds that phase to the 1 1, the 90 degrees phase Y. So so we're getting into, okay, so we're getting into, we put this into superposition and we do a T. So let's take a look at how this looks like here. So basically what we're doing in here is assume this is fixed. So for the element in the superposition that's not correct, we're not doing anything. We're rotating here. So we're rotating there where the output has a 1. Okay. If this was a 1, you'd still have that's interesting. It's a different rotation now. It's okay. Let's just focus on this case. So we've got a 45 degrees. Then when you do a control knot, you're basically so you're basically bringing the phase up here. Then undoing. You shouldn't take a look at this from an undoing perspective, though. Then the other control knot comes in there. So there's a game here being played with kickback, with phase kickback, seems like. Then this looks like that. And so basically you do a Hadamard again, but you've got 90 degrees and here minus 90 degrees. Need some more coffee. Okay, I'm back with more coffee, so let's get rid of these again. So let's start intuitively speaking, what's going on here? Because I see there's a pattern. There's one, sorry, okay, so there's one pattern in here, which is basically we are getting into, intuitively speaking, we're putting the so the algorithm is putting the target qubit into superposition, right? And then I guess the strategy. So now we've got basically um, we've got a superposition of our existing inputs, right, and then all the possible outputs, um, correct ones and incorrect ones, right? So in this case it's just two, right, because we just have two qubits in here. So we have like a 0 1 1 or 1 1 1, right? And I think the strategy here then is, okay, how do we now use the input qubits to get rid of the elements in our superposition that are illegal, right? Or that they are not valid outcomes of what we're trying to implement, which is this Toffoli. So by applying a T-gate, right, we're rotating. So we're rotating the component of we're rotating the component. We're rotating the elements in the superposition that have a 1 as an outcome, right? So that's rotated if we compare here. So now we've rotated that. But we still don't know, like let's assume we don't know that we've got a 1 1 here, right? Let's assume this is something that we don't know. So this doesn't still, it's not telling us, it's not, we're not assuming this is the correct one and this is the wrong, the invalid one. We're just saying we've got to differentiate those elements within the superposition. We've got to differentiate the elements that that have got a 1 as an outcome in the target versus a 0. Now comes okay, now let's try to intuitively understand what this control knot is doing in here, because there's different ways you can understand a control knot, of course. So let's try to do this with the conditional interpretation, right? So if this is a 1, or for all the elements in the superposition that got a 1 in here, right? Which means that we should definitely apply a knot in our target, because that's what we're going to do. If all the inputs are 1, we apply a knot in our target. So if here there's a 1, then we go ahead and apply a knot. Okay. What this will effectively do here is it will just, exchange those elements, really. So this will become 1 1 1 and this will become 0 1 1. So we apply a knot, because this seems to be more of an uncomputation step. So we apply the knot. We apply the knot basically, and yeah, that's they basically they've been changed. So now we've got, okay, so now we've got, what the way you could take a look at this is that now, okay, so now the states where the elements of your superposition that have a knot applied actually have that phase. That's maybe not, that doesn't seem so wrong. That's interesting. So you're basically saying the elements in my superposition that have a phase of 45 degrees are elements where I have applied a knot. Based on that qubit in here. Because it seems like that this part is trying to do the same kind of, right? But for the other qubit. Interesting. But now how can we understand that t dagger, so t minus 1 here? So for the solutions where we're going to have a 1 in here, we uncompute that. Okay, so if we uncompute that, okay, so it's almost like we're uncomputing these, right? So yeah, we're saying we're now we're saying we're going back to square one. The thing is here, it's the seeing the values actually it's bothering me because seeing these it bothers my current mental process of trying to understand that intuitively. We can think of this as an uncompute step of these. So what we're saying is that what we now have got is we've got an actual relative phase of 90 degrees between the solutions that are correct and incorrect. That's what we've introduced. So we have faced basically it seems like it almost seems like the control knot has been applied. Maybe I shouldn't see this as an uncompute. I should see these as I should see these as something in conjunction with that control knot here. Where I say let me go back to go back to the uncompute interpretation of it. So I mean that's what we got now. We got this. I mean here we are getting here we have a 45-degree phase between the elements that between the elements where I have applied a knot or not, like a control knot, like a knot or not. So by applying that, because remember that, I mean, the whole thing is when we will be applying the Hadamard at the end, we want that qubit to collapse to being like a 1 or a 0, which effectively means that what we want to achieve is that for the combination of 1 1 in here, we want that plus state to have turned into a minus state. So this means we got to rotate 180 degrees, so we got to rotate exactly 180 degrees. So this means after applying that first part of our strategy, we want to be 90 degrees away, right? Because then for the other qubit, we want to do the other 90 degrees. Maybe that's the reason this works. But it seems a bit unintuitive that, because I would have said I would have applied like a t and not like a minus. Like, what if I? Yeah, but if I apply a t, then we're back in where then there's no between those two elements. There's no phase difference, and we want to create that phase difference, but. And we have to apply the inverse because we've applied a knot. Probably that seems a bit tricky to grasp, but it's So it's not really an uncompute. This is to complete that 90 degrees difference that you want between the wrong solution and the correct solution. Remember, the strategy is we want to, for those cases where it's really the same concept with that I use with the controlled square root of x gates, where you're saying you want to start rotating based on the inputs in here, in a way that each thing here contributes, like if it's 2, that contributes to a half rotation. So if they're all 1, then you've got like a full rotation. But you gotta correct for those input combinations that's not correct, right? So if you start rotating half x here and then this is 0, then you should kind of correct that. Now, and I'm assuming that's gonna be what this last bit here is doing. This part. Exactly. I think that's what this part is going to be doing. That's going to be the correction. Yeah, of course. I think so. Because essentially what the trick here is you want to reduce, you want to use as less. Why don't you do that with... Okay, the only reason you probably don't do, because you could do that. Could you do that with... I'm not so sure if you could do that with x to like x to the power of like a 4th gates, or even like the square root of naught. But I guess the point is that the square root of naught, it's not something that I guess that's something that's not native, and it probably requires a U3, and that's the idea here. Is it requires in a... Well, yeah, that's probably what the M here is it's not using it's using rotations. Okay, but are they really Y rotations? I think there should be X rotations. Okay, we'll see. We'll take a look at these. But basically, yeah, so the only... You could do it this way as well, but then it will require U3 gates, which have a higher single qubit error rates, I assume, based on what they're saying here. So optimally using T gate seems to be the one that creates the less amount of errors, but that's the idea. So this seems to be the I think we're onto something here. This seems to be the correction beat. This seems to be the correction beat. Yeah. And so exactly. So now what happens is now we've kind of finished the contribution of that qubit into the whole thing. So we're here kind of. And now we're doing the other part, which is the same here. I mean, I get it. This t-1 is not... It's kind of an in-between step. You need that. You need that to make sure you have a 180 degrees rotation before you hit the last Hadamard. And so here you apply a control knot, and what this control knot is doing... It's basically... Well, I'm gonna clean that up. It's so effectively that's gonna swap this, but I don't like much to see it this way. It's applying a control knot. How did I say... What did I say here? I said if the way this acts is intuitively, you can think of these as, after applying these control X gate, the gates that... the elements that have a control knot applied have that phase of 45 degrees in here, which then turns into a 90 degrees difference between the incorrect ones and the correct ones. And so, and now when you're applying this control knot, now you're saying because now the difference is so now the difference, so here is minus 45, 45. That's, if we think this is rotating counterclockwise, it's either you could think of this as a 90 degrees, exactly, and now when you have that, here the difference is say bigger, right? But in the correct one, so that would be 180, that would be like 270 degrees. Exactly, 270 degrees, and so we've gone too far. So you need to apply a T-gate to correct that. Poof. And now, so you need to apply a T-gate to correct that, and now you've got why don't we apply an S-gate here? Wouldn't that work? If we apply an S-gate, I'll try later, because now we've reduced the gap, and so now so if now you know, if now we're just going to say, okay, we're done here, I mean that would work for this case, right? Because it will work for the 0, 0 case, and it will work for the 1, 1 case. Because now if I just say I ignore this last part and I apply a Hadamard and I measure, that should work. Okay, not entirely. There's still, it almost works. There's still that little part in here. Almost works. If this, I mean, but that's my point. If this was an S, or no, sorry, if this was an S, now that would work. Yeah, now that works. I mean, and it does have a phase, but now works. Why can't that be an S or two T's? Because maybe then the correction part doesn't work. So now again, that works for the 0, 0, 0. Oh, it doesn't work for the 0, 0, 0. Maybe that's why you need a T in there. Why it doesn't work for the 0, 0, 0? Tell me. Because there's an S. So that's why there needs to be a T in here for the 0, 0, 0 to almost work. Okay. Okay. But you still need that. Okay. But it's not perfect, really. So the T makes it work for 0, 0, 0 as well as 1, 1, 1. Anyway, this was just a test. So and now the issue, this is for the 1, 0 case, or the 1, 0 or 1, 0, like 0, 1, 1, 0 case. This doesn't, I mean, that works. That simply works. So that is a final correction for that little part. Okay, so I don't really get it why you need that part. It's I thought that was a correction for the 0110 case, but it seems it's a correction for, because now when you apply the control node again, and then here, mm-hmm, mm. Intuitively, what this is basically doing is, okay, so it's trying to cover the cases, right? So if we've got a 1 in here, trying to understand this intuitively, if we've got a 1 in here, and I know it's messing up a lot to have all these measurements in here, but mm, until that point we've got the cases where we've applied a control node have 45 degrees difference. Then we rotate more here and apply another control node. So what we have at that point is that, of course, it's a correction for the 1-1 case, of course, and for the 0-0 case. Because basically what we're saying is, now for the cases where there's a 1 in here, there's going to be these 90 degrees difference, or 270 difference, however you want to see it. But of course, the actual case, this is the 1-1. It means we've applied one control node too much, because we've applied it here and we've applied it here. So we want to correct that. Yeah. I think that's the logic. I think that's the strategy of this whole thing here. See, and so in this case, then you're applying a T and undoing, but for example, could this work? Yeah, I think doesn't matter which control bit you use. You're basically saying if you've applied both of them, then you need to undo one. Is that what you're saying? But then for the case of, say, 1-1-0, why does this work at all? So 1-0, what this is saying is 1-0, right? So we're going ahead in here and we're applying a control node. So now we've got the elements that have a 1 in here, and we have so in the elements where we've got where we have actually applied the control node are not, okay, in this case they are not phased, because this basically again corrects that, so we end up in the same state actually. But now this part here doesn't happen because there's a 0 up there, and so the difference in here and so the difference in here stays the same, and so okay, but then that indeed acts as a correction. Oh, it is not that straightforward, but I think I'm not far away from an intuitive explanation of these. It feels like it's the same strategy. If this is the case, now we got a 45. So now we got a 45 45-degree phase in the case of got a 45-degree phase in this case. This for the one case, for the one output. It somehow needs to pick the correct one. So and then we're doing this so nothing happens in here. And so that thing basically corrects the T. And so we're back here. Here, kind of nothing happened. There's no visible effect in this case. And then that T here, that T here in conjunction with the control, which doesn't happen, and then there's a correction. So it almost feels like the control nodes are kind of so we're using control nodes to pile up those rotations somewhere. I think that's why I'm trying to find sort of a general way to describe that. At an intuitive level and without really touching any math. Because you could just do the math and then see that it works, but that doesn't explain you what's the mental strategy to build something like that. For the 0-0 case, I mean, those two qubits, nothing's going on with them, and so you just get into superposition, apply a T, correct it, apply a T, correct it, you're done, right? Exactly. So that's what I'm saying. It's basically applying, correcting, but the control X's in here seem to be sucking that up, maybe because of the phase kickback. In a way that if we've got that particular combination 1-0, then we apply the T. Now we say, oh, okay, so there's a 1 in here, so let's apply the control X. Maybe that's the wrong way to say that. There's a 1 in here, so I want to keep that rotation. Maybe that's how you would do this. But then what does this mean? This means that if you want to keep that rotation, that T rotation, you're kind of swapping it. You're kind of moving that rotation to the part that has a 0 in here, and then you do these T-1 to actually create that effect, those 90 degrees in here, right? If we stop here and now we take a look at this case, then basically we can ignore this gets corrected with these. So we can ignore everything in here, and basically the same happens in here, right? Exactly. It's like it. Yeah. Wait a second. So you start like that, and then you apply these. No, sorry. Let me correct that for a second. This is what you should ignore. So you're applying these rotation t minus 1. No, but that gets corrected. You should ignore that as well. So the control knot here that's not visible, that has no visible effect. The T-gate will rotate that one here. But because you don't have a 1 in here, that will then just self-correct here and give you that state that just, you know, goes back to it's like the original state. Exactly. Now when you've got a 1 1, this is where it gets interesting. You apply that T-gate in here that does a 45-degree rotation. The control knot here, because there's a 1, say I want to keep that rotation. I'm still struggling with this. I want to keep that. I'm just saying I like to think a bit more as intuitively. This has to stay. Intuitively, you're saying, okay, so I apply this rotation, and because there's a 1, I apply a control knot, which is my final desired function. That control knot, it's applied in both cases, right? Of your superposition in this case. You know, here and here, right? Now, I think I'm almost right. I think I probably need to refine this a little bit. It's been already like a pretty long video, but I think I get the gist of this. I'll probably do another iteration on this, but this seems to be the case. This seems to be exactly this. So and then you're doing the other. So you're doing this here. That's creating this 90-degree or this difference. Because your target should be that you get. Your target should be exactly. Your target here should be. That's what I said in the beginning. That the difference between the correct and incorrect elements is 180 degrees. This is plus 90, this is minus 90. Why? Because why? I mean, you've got a minus in here. That's the whole point. But you still want to have that 180 degrees difference between the states, so they collapse cleanly by the Hadamard. Yeah. So ideally, you would have like 0 and 180, because then that would not give you that 90-degree phase in here. But what they're saying is, what the paper is saying is like, honestly, as long as the correct and the incorrect are separated by 180 degrees phase, we're kind of, it's good enough. Then we can correct these. It's like it's good enough, because then at least we get a clean result. So it's this 180 degrees difference you want to create in here, and that you're doing step by step by saying, okay, now I apply 45 degrees, then I apply control knot, and then I kind of, if there's a 0, right, I just want to correct that back. If not, then I want to keep that control knot. sort of a way to see this. It seems to me that the rotation, the controlled M, the art of M, is probably easier to explain. The Novatofli operation, the sign of is inverted. This gate uses 4 U3 gates. It's easier to explain, seems to me. Maybe not. Y rotations, okay. But I'm kind of missing that a little bit. That kind of intuitive little step. Maybe a better way to phrase it is like that. So you're using these phases here to sort of encode the fact that you've applied a control knot. So for every 45-degree thing that you're encoding in here, it means, okay, I have applied a control knot. Now, if that input is 0, you're not going to apply the control knot, so you basically, the phase you've added here, you're undoing it. Exactly. Now, for the case this is a 0 and this is a 1, you're kind of going to have... So here you don't need, because of the fact that the control knot here won't have any effect anyway. Anyway, so that's the point. If there's a 1 in here, you want to keep that. So basically, by design, you're keeping that phase in your superposition. It's like those two elements have a difference of 45 of 90 degrees at the end after these, because you have actually applied a control knot. Yeah. And so the same happens here. If that control knot really takes place, because there's a 1, then you're going to increase that 90 degrees, and you're gonna you're gonna have you're kind of increasing that, exactly. But if not, right? If this is a 0, then this control knot doesn't happen. This T kind of cancels out with this one, but which still means, okay, exactly. That's why you're doing this. Okay, so you're basically saying, if that doesn't happen, then this this T kind of corrects this one, but you still have got this part here that you've applied a control knot because of this one. So you got to correct that, and then say, and then you're uncomputing that actually. Yeah, you're actually uncomputing that. So that's really like you're uncomputing this thing here. Okay, interesting. Yeah. In this case, you're saying, okay, so if this was really a 1, and I really haven't applied this one here, then I want to get rid of it. So you're uncomputing it regardless. So you're saying we start over here, we apply a T gate, and then because there's a 1 in here, this operation is going to leave, like in conjunction with this one, it's going to leave a phase difference. Now we apply this one, which is going to have the same effect. It's going to add more difference, and then we kind of correct regardless, and that's why you're not getting the like 0 and 180 degrees thing. But it's the same concept. This seems to be this. I'm not like, I feel like it's 90% this way. I'm not like 100% convinced this is intuitive enough. But roughly, right? You get the idea. It's like you add a little phase, and if you shouldn't apply a control knot, you correct. And then you're using the fact that you've added already something in here, so you're doing the same for the other qubit, and then you kind of at the end you're correcting that anyway. Yeah, I think that's it. Okay, I think we'll leave it here for this video. it's been a pretty long one, I think, but I get a sense of the effect here. So I think you could correct that now probably by applying some other operations, and that's kind of would lead you to a full Toffoli implementation that respects the phase and doesn't have that 90 degrees phase effect at the end by adding maybe one or two more control nodes somewhere. I don't know. Okay, and the control and the RTOF M, it needs U3 gates. U3 gates. Okay, I'll take a look at. But it's basically the same concept. I see. Okay, so you're not applying a Hadamard, but you're applying Y rotations, and it's the same concept. You're okay. So you're kind of but again, I think it shouldn't be RY. It should be Y, like the Y gate, right? But you're basically what you're gonna do in here is you're applying the rotation, then the control knot, then another rotation and the control knot based on the fact that you're trying to see how much those, like whether those things are really ones or not. And then in case this was a 0, for the cases where this is 0 and this is a 1, because you've applied that, you got to basically uncompute it. Yeah. For the cases where this is a 1 and this is a 0, then nothing happens anyway. If this is a 1 and this is 0, nothing happens anyway because you haven't applied any of these. So these and these basically cancel out. So nothing happens in here. Yeah. So that's it. Okay. So I'm not going to dive into this one just to make sure that I manage somehow in a timely manner to go through all the paper. But we can take a look at this later on. I mean, but it's definitely the same concept. It's just you're not getting into the idea here is by applying a Hadamard and then T's, you're able to use native operations of the quantum of the QPU in this case, because the T gates can be implemented with U1 gates, I assume, with the IBM architectures or IBM computers, which have lower error rates. Whereas if you do it this way, you gotta have like U3 gates, which are those like I think those are those rotations with 3 degrees of freedom, which are probably more error prone. But it's the same strategy. Pay attention; it has the same thing, the same structure. Okay, cool. So now we understand the RTOF intuitively, kind of. And then the next part would be to understand the Toffoli with a swap circuit built in. Okay. Seems like this seems to me like this is the following a similar strategy. Then there's a swap, and then there's some kind of correction of whatever, I don't know. So this seems to be this. And so on, by adding surrounded by a broken line. But why? Why is this important? If the processor can embed the structure shown in figure 12, the procedure can be executed without additional swaps. So this is maybe needed because of a particular architecture or a particular connectivity configuration might require you to have a swap in here. Maybe. Okay. Okay, so I will dig into this in the next video, why that swap needs to be built in there. Okay, but then it's again experiments with the IBM Q devices. Okay, performance and stuff like that. That's gonna be interesting. Okay, but once this is done, then basically we can take a look at how this amplitude amplification plays together with this part in here. with the virtual vertex and the oracle that we talked about. We've learned so far that there is a way to implement that oracle in a way that it gives us the right solution, but it also gives us a couple of other solutions that are not right, but they are obviously not right. So you don't really need to worry. You know that the no cat solution is it's not your solution. And then you've got basically an amplitude amplification here that has the challenge of the challenge here is how do you implement the Toffoli gate in a way that you can really implement it in the reduce the errors, and so reduce the amount of control X gates, reduce the amount of U3 gates and stuff like that to make sure that there's as less errors as possible. And so you've got this little trick in here. And it seems like it's about making compromises and saying, okay, it's not gonna be a perfect Toffoli gate. It's gonna have that little dirty effect at the end with the face, but we can correct it. Okay, let's see how that ends. How we put all the pieces together. But that's cool. Cool.